So today I want to talk about mostly about Miller algorithm. I'm not sure we will finish in this session, but at most in the next one, I think. But to set the stage, there is one more thing that we need to discuss, and the issue is that you remember in for two n torsion points, we defined En of PQ to be GQ of P plus S divided by GQ of S, where S is some point on the curve, and it turns out that it does not depend on the choice of S. But the function GQ is defined by a divisor relation. Let me just recall this. Yeah, so this the divisor of GQ needs to be the sum of over all n torsion points R of bracket Q prime plus R minus bracket R, where Q prime is an n squared torsion point such that nq prime is Q. But this is not so easily computable, and in fact, there is something else that appears in the construction of the Weil pairing that is easily computable. So yeah, so that's not easily computable. But we can compute fp, a rational function on E, such that the divisor of fp is n bracket p minus n bracket o. Now, okay, this statement you should not be convinced by just me saying it. We will see soon enough. This will be the Miller algorithm, but let's say intuitively, you can imagine that it's much more feasible to try to compute fp than to compute GQ. Okay, so we want a definition of the Weil pairing that involves FP instead of GQ. So we want a definition that oh, so it should be easier to compute FP, and we want a definition that involves FP and not FQ and not GQ. So, so what do we do? What happens is that there are several equivalent definitions of the Weil pairing. And this appears in the section equivalence of definitions of Weil pairing, is 6.12 in the notes. And in fact, I mean, we will not have time to show that the definitions I give are indeed equivalent to the original definition we saw of the Weil pairing. But I can tell you what is the main ingredient. So basically, so for a divisor D, which is some sum NP P runs over all points. Its support is support of D. It's a subset of the set of points on the curve, and it is defined to be the set of points P such that NP is non-zero. In other words, it's the set of zeros of well, yeah, the set of zeros of D union the set of poles of D, right? Because anything else is not. So this zero and poles really mean, I mean, zeros are points for which the coefficient is positive, and poles are points for which the coefficient is negative. And I can also do this for a rational function. So for R, a rational function, its support is support of R is the set is again it's a subset of the set of all points on the curve, and it's the set of zeros it's the set of zeros of R union the set of poles of R. And now suppose D is a divisor on E, and R is a rational function on E, such that the support of D is disjoint from the support of R. Then we can evaluate R at D. And the way to do it, so let's say D is this finite, this sum NP bracket P. D does not need to be a principal divisor. It can be any divisor that has support that is disjoint from the support of R. So the set of zeros and the set of poles, the set of zeros and poles of D does not intersect at all with the set of zeros and poles of R. And then we can do, if I want to evaluate R at a divisor D, I do a product of R evaluated at P to the power of NP, where P runs over all points. And you see, this is a finite product because in D, there are only finitely many points P that for which NP is non-zero, and R cannot become zero or infinity for any of the points in the support of P. So whenever this term is always defined, we can say that R of P, whenever P is not in the support of D, it means that NP is zero, and we know that RP is finite and non-zero. So I can always say that something finite and non-zero to the power of 0 is 1. And therefore, this sum is, this product is always well-defined. Any questions about this evaluation? Is this clear? Is this?
I think this is for me the definition of RD is clear, but I'm just a bit confused why you wrote a little bit before support of D intersection with support of R. R is a rational function; it's not divisor. So what do you mean by support of R here? Is not clear to me.
Yes. So this is sorry, I should have said the support of D intersection support of R is the empty set.
Ah, okay.
But okay, so this is disjoint support.
Ah, sorry. So you define the support of R just below before. Okay, no, so makes sense. Okay.
I mean, the support of R and the support of D is defined in using the same principle. It's like the set of zeros and the set of poles.
Yep.
Okay. I mean, for a divisor, we don't formally say that a point is a zero or a pole, right? Because it's not like this divisor is not necessarily a principal divisor. But we can just extend the definition by saying that for a divisor D, any point that has a non-zero coefficient, right? This any point P for which NP is non-zero is either a zero or a pole. If NP is positive, we can say that that P is a zero of D. And if NP is negative, we can say that P is a pole of D. Okay, Nicolas.
Yep.
Now, what do you think? Are you okay with this definition?
I think so. Yes. Thank you.
Yeah. So you see, alternatively, this if you don't want the complication of like running over potentially infinitely many points, we could say that RD is the product over all RP to the NP, where P is in the support of D. Okay, so this by definition, I simply define the sum in orange, sorry, the product in orange to be the product in purple. Okay, so and the product in purple is always defined because of the condition that the two things have disjoint support. Because otherwise, if I don't have this condition, it could be that that P is a zero of R. But it's a but if it's a zero of R, so if P is in the support of D, so it has some let's say a positive coefficient, and then it could be generally that P is a zero of R. If P is a zero of R, then R of P is zero, and I don't know how to evaluate R of P. I mean zero to to some positive exponent, and also if P happens to be a pole of R, then R of P is infinity, so R of P to the NP would not be a finite element in the field. But in this definition, under the green condition, I can always assume, I always get that R of D is an element in K. It's not infinity and it's not zero, in fact. So it's an element in K that is not zero. And using this evaluation, well, first, I guess I should say, this is the main component to show that the two, the definition that I will soon sketch or write is equivalent to the original definition is called the Weil reciprocity. And this says let R and S, well, S let E over K be an elliptic curve with a K algebraically closed. Let R and S be rational functions such that the support of R is disjoint from the support of S. Then, if I take R and evaluate it on the divisor of S, I get the same thing as S evaluated on the divisor of R. And this result, it's a very nice symmetric property of elliptic curves. I guess R and S need to be non-zero rational functions. And you could, we unfortunately do not have time to cover the proof of Weil reciprocity, but you can look in the notes. There is a proof for Weil reciprocity over the projective line, and it's not a big deal to translate the proof of the over the projective line to a general curve. So this is in fact a property of rational functions on any algebraic curve. And we will skip the proof of Weil reciprocity and get right to the other definition of the Weil pairing, and this goes as follows. So suppose D is a degree 0 divisor such that ND is principal. So, for example, you can take an n torsion point P and D to be P minus O. The divisor D is not principal because can anybody say why D is not a principal divisor? So this is anybody remembers what is a principal divisor?
So the degree and the sum should be 0?
Yeah, but for this divisor D, what is the degree of D?
0.
0. What is the sum of D?
P.
P. So D cannot be principal, right? P, let's say P is non-zero, I should say. P is not the 0 point. Then D is not a 0, is not a principal divisor. But so D not a principal divisor, but ND is NP minus NO. And this is a principal divisor, right? You see why or now?
Yes, because now both are 0, like the sum and the degree.
It's because because I took P to be an n torsion point. So so then this thing is going to be NP minus NO, and NP is assumed to be 0.
Cool.
Okay. So I take some divisor of degree 0 that such that ND is principal. By the way, we also write that ND is equivalent to 0. Yes.
What do you mean here by equivalent?
So we can, when we talked about divisors, we defined an equivalence relation by saying that two divisors are equivalent if their difference is principal.
All right.
Okay, so to say that something is equivalent to the zero divisor is to say that, well, this something minus the zero divisor is principal, which is just saying that this divisor is principal. Okay.
Yeah, thank you.
So suppose D is such a divisor for which ND is principal. And let FD be a monic rational function such that the divisor of FD is is ND. Monic here, I would just say it means that the leading coefficient of FD is 1. We had some propositions saying that you don't have to remember what is the leading coefficient. It's a bit of an irrelevant detail, but we had a proposition saying that I mean a function that has a divisor, some prescribed divisor, is completely determined by the leading coefficient. So if I choose the leading coefficient to be 1, and I say that FD has to have a divisor ND, then FD is completely determined. There's no ambiguity. And now I can do the construction, I guess. So for P and Q and torsion points, choose divisors dP and dQ such that 1, the support of dP is disjoint from the support of dQ. And 2, dP is equivalent to P minus O. dQ is equivalent to Q minus O. And actually it follows, if I can find such divisors dP and dQ, it would follow immediately that n dP is equivalent to 0 and n dQ is equivalent to 0 as well. Can anybody see why the orange implication is true?
I'm not following this part.
Because P and Q are part of En, no? So
yeah, exactly. So to see why the orange implication holds, I mean, suppose I have a divisors dp and dq. Each of them is equivalent to, well, dp is equivalent to p minus o. What does it mean? It means that dp minus p minus o is principal. It's equivalent to 0, hence principal. But I mean, if dp is I mean dp minus p minus o is principal, I take n dp so I can kind of multiply everything here by n. So and this will remain an equivalence. I mean, I do n dp minus np minus no is going to be equivalent to n0, but n0 is 0. So it means that ndp is equivalent to np minus no, and np minus no, because p is an n torsion point, this is a principal divisor. And the same goes for dq. Is this better now?
Yes. Yes. Thank you.
Okay, so this is like just you can think of it as a formal issue, but there is a subtlety. I mean, why cannot I choose dp to be equal to p minus o and dq to be equal to q minus o? I mean, this surely if I choose dp to be p minus o, it has to be equivalent to p minus o, and dq I can do the same. So why do I need I mean, why can't I choose dp and dq to be in this simple form?
I think I'm confused.
Can you repeat again what you want to know, what you can do?
Yeah, I mean, I want in this the beginning of this construction is like it says choose divisors dp and dq that satisfy these two conditions. So to satisfy the second condition, I can simply choose dp to be p minus o.
But then this is not principal, right?
I didn't say that dp is principal. Only n dp needs to be principal.
Which is what you showed in the previous section.
Yeah, but why can't I choose really dp to be equal to p minus o and dq to be equal to q minus o? This surely it satisfies the second condition, because any two divisors that are equal are necessarily equivalent.
Okay. Oh.
The issue, do you have an idea, Nicholas?
So yeah, I still don't quite get what is the question exactly. I understand
the
what you're
question
saying
is,
now about dp and dq and
can I
dp,
choose? I mean, this in this construction, we say we take some two n torsion points p and q, and we say that we choose divisors dp and dq that needs to satisfy these two conditions. Now the question is, can I choose dp and dq to be simply p minus o and q minus o? This will be the ideal scenario, right?
Because I don't think we can, because the zeros are the same, right?
Exactly. The support is not disjoint. Okay? You see this or no? What is the support of dp?
I think I'm missing this.
So support of dp is a set of 2 points. It's p and o.
So it's the zeros and poles. Okay, okay. Yeah.
And the support of dq is q and o. So they have a common element in the support, which is o, and that's not so this is no good, because it would not satisfy condition number 1. Okay, so this choosing a pair of divisors like this is a bit tricky, but I will soon show you how you can do it. And we define let me call it a generic or general Weil pairing as En generic of P and Q is you take I didn't sorry, I'm missing something. So let FDP be a monic rational function such that the divisor of FDP is NDP. Can you see why there is such a function, FDP?
But didn't we look at we looked at this some time ago, so I don't remember clearly, but we looked at how to construct a function which has a specific divisor.
No, we didn't. We still didn't show a way to explicitly construct FDP, but I'm asking, why does FDP? How do I know that such FDP exists? I mean, it's not true that every divisor comes from a rational function.
Yeah, but NDP is principal, so it comes from a rational function, no?
Okay, it's because NDP is principal. It's equivalent to a principal divisor. It means that it's principal. And similarly, FDQ, such that the divisor of FDQ is NDQ. Now, Lisa, do you follow?
Yeah, it's fine.
So I have a question. So in the previous part, right before in the orange part, is it correct that so you say that since their support is disjoint, we cannot use dp equals p minus o?
Mhm.
by the formal subtraction of them. But we can use, instead of equal, we can use equivalence, and then the disjoint support is 0 again.
So what I can do, let me write it in another color. I can take dp, for example. I will soon get into like explicit details, but let's say I take dp to be p plus r minus r for a carefully chosen r. Then I claim that this dp is equivalent to p minus o. But now it can, I mean, if I choose r carefully, it can be it can have a disjoint support than dq. And let's say I take dq to be q minus o, okay?
Okay.
And dp I take p plus r minus r. Why is p plus r minus r equivalent to p minus o? It's because let's say dq is q minus o, and dp is p plus r minus r. And then dp minus p minus o is, by definition, it's a p plus r minus r minus p plus o, right?
Yeah.
Or let me just write it a bit more formal. So this, and this thing is a principal divisor.
Mhm.
Because the degree is 0, right? I have like 1, minus 1, minus 1, and 1. And if you sum all the points, you get also 0, right?
Yeah, nice.
Okay, so you see what I did here, in order to satisfy both conditions, I can take one of the dp and dq to be this either p minus o or q minus o, but the other one, the dp or the dq, I need to shift by something. And well, I still didn't finish the definition. Now you will see, I guess, the full picture. We define the general Weil pairing of P and Q as En generic of P and Q is FDP evaluated at DQ divided by FDQ evaluated at DP. Okay, where this thing, I remind you, FDP, when you have a rational function and you want to evaluate it in a divisor, let's say dq if dq is q minus O, then I assume that f dq is a rush. Sorry, so this is f dp. I assume f dp is a rational function whose divisor is ndp. So it's the support of FDP is disjoint from the support of DQ. This is because by assumption the support of DP is disjoint from the support of DQ, and the support of FDP is the same as the support of DP. So this is then going to be F dp evaluated at Q times F dp evaluated at O to the minus 1. Okay? Any question about this definition? This is like it's a bit abstract, but I think it's very useful to have, and we will soon get into more concrete choices, and I will show you how to choose this DP and DQ easily. But I think it's useful to really phrase it in the most general way, because it has a nice symmetry to it, and you don't see the symmetry if you go to the concrete definitions.
Is this a statement, the last line you wrote? Because I don't quite understand why or how you came up with this. Why is it times FDP of 0, the inverse of it? Where does this come from?
Because what does it mean to FDP is a rational function and DQ is a divisor, right? And let's suppose that DQ is Q minus O, equal to Q minus O, okay? So I'm just like repeating, what does it mean to take a rational function and evaluate it on a divisor?
But this is your definition. This is just like we're gonna say that evaluating a rational function on divisor is this way.
I mean, the general definition is if D is sum NP bracket P, then and R is some rational function, then R evaluated at D is R of P. Well, it's the product R of P to the NP, where P runs over the support of D.
So the minus 1 comes from here, the NP, because it's a 0, so it's minus 0, so it's minus 1. Okay, that's what I get. Okay, thanks.
Do you see this or now? You see why the green thing is, I mean.
Yes, thanks for the clarification on the, like what you just said, because I was also missing the minus 1.
Yeah. Yeah, so this is exactly how it goes, but the generic definition of the Weil pairing, as here in the orange box, it is very convenient for kind of theoretical manipulation, because it's symmetric. And I guess after the break we will make a few choices of DP and DQ, and then we will be able to apply the Miller algorithm. The Miller algorithm will calculate, I mean, if you think of it, FDP, let's say if DQ is Q minus O, then f dq needs to be a function such that the divisor of f dq is n dq. And let's put it here. The divisor of f dq needs to be n dq. And for this choice of dq, it's going to be nq minus no. And this is what I said in the beginning of this session, that functions like this, we can compute with the Miller algorithm. So, I guess it's a bit more, it could be a bit more clear now that using this generic definition of the Weil pairing, we have a better shot of calculating it. Now, one thing I want to say before the break: how is it going to be? How do people prove that the generic Weil pairing is equivalent to the Weil pairing definition that we saw in the previous sessions? We use Weil reciprocity, because here I can instead of FDP evaluated at DQ, I have a function. Well, okay, so let me not spare the details, but basically, let's say theorem for any P and Q. En PQ is equal to En generic P and Q. And the proof is an application of Weil reciprocity. Okay. So let's take a break and come back to the Miller algorithm. Okay. So before I go to the Miller algorithm, I think it's nice to know a bit of the story around it. Essentially, essentially, Miller was able to come up with an algorithm to compute FP evaluated at Q, let's say. For FP that has a divisor NP minus NO. And he sent it to a lot of journals. He thought that it's an interesting. I mean, he can compute it in an efficient way. Basically, log n, I think log n of additions of points on the elliptic curve. And each addition of the point of the elliptic curve is not too complicated. So eventually it runs in polynomial time. And he sent it to many journals and got rejected. And the rejection reason was that there is no application. So eventually the paper was published in 2004. Where it took him like 6 or 7 years to get it published, and now with zero knowledge snarks and the rest of it, pairing-based cryptography, Miller algorithm is the most central computational tool. I mean, the only way basically that we know how to compute pairings efficiently is using the Miller algorithm. So it's kind of a nice well, I mean, important thing to know when people tell you that something has no application. It can be just overlooked, and I think the cryptography community is now more aware of such phenomena and more open to new things that do not have immediate application. Yeah.
I have an education question. Can you explain when we write FP and when we write FDP?
Yes. So FDP. So FDP is a function such that the divisor of FDP is NDP. And DP needs to be a divisor that is equivalent to P minus O. So NDP is going to be equivalent to NP minus NO, but only equivalent. Means that if you subtract the two divisors, you get a principal divisor. I mean,
Right.
okay. So FDP is a bit more general, but for DP that is equal to P minus O, FDP is exactly FP. Okay.
Okay.
Now, what we're going to do is a geometric construction. So geometric construction. And we go back to lines. So suppose I have 2 points, U and V, on the curve. The line between U and V is a rational function such that the divisor of LUV is U plus V plus minus U plus V. Well, sorry, I need some more space. The divisor of LUV is U plus V plus minus U plus V minus 3O. So here I assume that U is not equal to V, and both U and V are not the 0 point. And then the divisor of, I mean, LUV, it's like the line of the, I mean, the line that passes through U and V. So if this is U and this is V, then somewhere here is going to be minus U plus V, because U plus V is taking the intersection and reflecting it. This is U plus V. So this guy is minus U plus V. And if I take the green line, if U and V are generic, I mean they're not the 0 point and they're not equal to each other, then what is the divisor of this line? Well, I need to count the number of zeros and the number of poles. So how many zeros does this line have? It has a 0 at U, it has a 0 at V, and it has a 0 at minus U plus V. All of them, I mean, because it's a line and the elliptic curve is a degree 3 curve, it can only have at most 3 zeros. So all of them have to have degree or multiplicity 1. And then since I know that this is a rational function, I know that there has to be a pole of multiplicity 3. And this pole has to be the point at infinity. Right? I mean, that's kind of the consideration that we did in a while ago. Now, for the case that U is not equal to V, but V is equal to 0, this the divisor of LUV is going to be U plus minus U wait I guess for u equal to v. Sorry. Yeah, so for u not equal to v, but v is equal to 0, what I get is the divisor of LUV is u plus o plus minus u plus 0 is minus u minus 3o. So this is equal to u plus minus u minus 2o. Okay, and then so this is u not equal to v, but v is equal to 0, and similarly, if u is equal to 0, then you get the same, but with v. The tangent line at u is a rational function t u such that the divisor of tu is equal to 2u plus minus 2u minus 3o. And the picture here is similar. Let's say I have some u here. Then I draw the line that is tangent to u, and this line, what happens? It intersects. I mean, this is 2u, and this is minus 2u. So this line intersects the curve in minus 2u. Now, because it's a tangent line, this we discussed, u is going to be a 0 of degree 2. This can be shown with uniformizers and so on. It's kind of a property of the tangent line. And so I know what are the possible zeros. The possible zeros are u and minus 2u. At u, I have degree 2. So it means that at minus 2u, I have to have degree 1. And then, since it's a rational function, I know that I have to have a pole of degree 3, and this pole has to be at O, because it cannot be at any other point. Is this okay? This tangent line and horizontal line, I guess.
Can you explain once again what, like for now, since the geometric construction, I feel like we introduced two lines, L and tau. That's it.
Yes.
Right?
Yes. And let me introduce the third one. I mean, I'm still in
Wait, but
this.
why is it horizontal? It's not horizontal.
It's like horizontal. I mean, it's not vertical. It's not. It's not going to touch the point at infinity.
Okay.
Okay. Yeah, I guess horizontal, or you can call it something else, but let's say non-vertical. Non-vertical. And the vertical line, so let VU be the vertical line at U. And let's draw the picture again. I have U, and I take the vertical line at U. So here is going to be minus U. And it's going to intersect the point at infinity. I mean, it's going to intersect the curve also at the point at infinity. So nu, this nu U has a divisor that has U minus U, O, and then minus 3O. So I might as well minus 3O. So I can just write it as U plus minus U minus 2O. Yes.
Sorry, I think you mentioned it again, and we already looked for it again. But where does this minus 3O come again?
So I have to have degree. This is a rational function, right?
Yeah.
So the divisor has to have degree 0.
Yep.
If I put, I mean, I check the degree before.
I just took coefficients. Yeah. Okay, sounds good.
Okay. So I have to have, and whatever I put, I mean, whatever point I put next to the 3, it has to be a pole, right?
Yep.
Now the only way to put this vertical line, I mean, the only way to get the pole is at the point at infinity. Yeah, I guess here it's a bit. Let me just write it like this. Yeah, I guess I gave some heuristic explanation, but if you calculate the vertical line, you get U plus minus U minus 2O. So, okay, so now observe for any U, I have a TU, which is the tangent line at U, is the same as the horizontal line of U and U. And if I take the vertical line at U, it's the same as taking the horizontal line of U and minus U. Okay, so this is by construction. It's like And now this construction for a P and Q and torsion points, and R and S two points on the curve such that S is not an element of the set R, P plus R, P plus R minus Q, and R minus Q. Consider the divisor dP to be P plus R minus R, and dQ to be Q plus S minus S. The basic claim is that these divisors have disjoint support. Support of dP intersection support of dQ is the empty set. And this is a routine check, but let's do it. I mean, if S does not belong to this orange set, so what are the I mean, the support of dP is P plus R and R, and the support of dQ is Q plus S and S. Now, R cannot be equal to S because S does not belong. I mean, S does not belong to the orange set. So these two are different. R can also not. I mean, let's do it like this. S cannot be equal to R because S does not belong to this set. Then Q plus S cannot be equal to R as well because S is not equal to R minus Q. So this is equivalent to say that Q plus S is not equal to R. So I have inequality here. Now S cannot be equivalent to P plus R. And this is basically this relation. And S, so S cannot be equivalent to P plus R. And S cannot be, okay. We said S cannot be equivalent to R, S cannot be equivalent to P plus R. Q plus S cannot be equivalent to R, equal to R, and Q plus S cannot be equal to P plus R because if Q plus S is equal to P plus R, this is the same as saying that S is equal to P plus R minus Q, and we took by condition that S is not equal to P plus R minus Q. Okay, so it's that's the end of the proof. Is this clear? This small issue? Okay, so now I define the Weil pairing. And of course, clearly, dp is equivalent to p minus o, and dq is equivalent to q minus o. Right? Because, for example, I do the dp case, dp is p plus r. This we basically showed before, but let me do it again. P plus r minus r, and I subtract from that p minus o. Then I get a divisor that has a degree and sum 0. So this is principal. Principal means that it's equivalent to 0. So this is the same as saying that the dp is equivalent to p minus o. And now I can use the generic definition of the Weil pairing. And of course, we take f dp such that the divisor of f dp is n dp, and f dq such that the divisor of f dq is n dq. And we know that the definition of the generic Weil pairing is that it is evaluating one rational function by the other divisor and taking the quotient. So En of the generic Weil pairing is f dp evaluated at dq divided by f dq evaluated at dp. But this we can, I mean, f dp yes, so so let me take we took dp and dq, right? So fdp and fdq, I know what their form is. This is ndp is equal to n p plus r minus n bracket r. So fdp, I can take it, I take it monic, and let me call it, well, okay. fdq needs to be n q plus s minus n s. So let me call it I do a little bit of use of notation. I call it FP, and I call the FDQ, I call FQ. And then the definition of the generic Weil pairing, I can simply write it as I take FDP or FP and I evaluate it at DQ. But what is DQ? DQ is like P plus R minus R. So this is P plus R divided by FP at R. This is the numerator. And all this I divide by FQ evaluated at, sorry, here, I apologize for it. This is FP evaluated at DQ is FP at Q plus S divided by FP at S. And here, this is FQ at P plus R divided by FQ at R. Okay, so this is what we need to calculate. And let us describe an iterative procedure to calculate FP of X for X in E. And this iterative procedure, so for K in Z, I let Fk be monic such that the divisor of Fk is K P plus R minus KR minus KP plus O. Sorry. So Fk needs to be a monic function such that the divisor is K P plus R minus KR minus bracket KP plus O. So if I take K equals N, then Fn is equal to Fp, right? Because Fn is going to be a function, the divisor of Fn is going to be N P plus R minus NR. And these two things cancel out because P is an n-torsion point, so NP is going to be 0. So I know that the divisor of Fn is equal to the divisor of fp, and since both of them are chosen to have leading coefficient 1, they must be equal. Is this clear?
I understand why the KP disappeared when k equal to n. Why the 0 disappear?
Because I have, I mean, it doesn't disappear, it becomes a minus O, right?
Ah, okay, that's right. Yes, makes sense.
Arnaud, do you follow, Lisa?
I'm kind of following on the technicalities, but yeah, okay, let's assume I'm following.
I can repeat. We will not finish the Miller algorithm today, so I mean I can repeat. I will repeat next time anyway. But basically, you see, I'm still in the reduction steps. I mean, I'm saying I want to calculate FP. Eventually, I want to calculate FP evaluated at X. If I can do FP evaluated at X, then I can, I mean, for any X, then I can choose X to be Q plus S, or I can choose X to be S. And if I can do it for FP, I can do it for FQ, right? It's completely, I mean, if I have an algorithm for FP, I have one for FQ, right?
Yeah, so whatever we were doing before we got this orange formula, we were modifying the formula to get the orange formula.
Yeah, I mean, so what we did before the orange formula is we chose, you see, we chose dp and dq in such a way that they would fit to the generic definition of the word pairing.
Right.
That is, they need to have disjoint support, and they need to satisfy this. Need to be equivalent to p minus o and q minus o.
Right.
And then we say, okay, so what is the generic Weil pairing? You take FDP such that the divisor of FDP is n times dp, and n times dp is this.
Mm-hmm.
Okay, and you take a rational function FDQ whose divisor is this. Here should be brackets, right?
Right.
Its divisor needs to be n times dq. So this is this, and then you calculate. So I mean, now I call FDP I call FP, and FDQ I call FQ. So you see from the orange formula that we need to calculate FP at basically at a general point.
Right.
Okay, so now I'm going to say I'm going to define a sequence of functions fk such that when k is equal to n, I get fp.
Mm-hmm.
And I will show you how to evaluate the functions fk at a generic point x. I will do it iteratively, okay? And once I do this, I'm finished. But first, I want to, I mean, one of the steps is some relation between the fk's. Before I do that, now, are you with us?
Yes.
Okay, so the proposition is the following: for A and B in Z, if I take the divisor of FA times FB times the line at AP the line between AP and BP divided by the vertical line at A plus B P, I get the divisor of F A plus B. Okay, it's a very nice nice relation between the various F's, FKs, and using this the lines and the the line and the horizontal and the vertical lines. So let's see how it goes. And the proof is very easy. You just unravel. I take the left hand side and I calculate the divisor. The divisor of a product of functions is the sum of divisors, and the divisor of a quotient of function is the difference of the divisors. And I know what is the divisor of FA, what is the divisor of FB, and I also know what is the divisor of this horizontal and vertical lines. So I can calculate. This is A P plus R minus AR. This is the divisor of FA. Then from that to that I add B P plus R minus BR. This is FB. Then I need to add the divisor of the line between AP and BP. The divisor of the horizontal line between AP and BP is AP plus BP plus minus A plus B P, because this is AP plus B plus BP is A plus BP. Yeah, but I forgot the O's. So here, okay, so the divisor of FA is not exactly what I wrote, but rather minus AP plus O. The divisor of FB, I need to subtract minus BP and add O. And then the divisor of the horizontal line between AP and BP, I have minus 3O. Let me write it here, minus 3O. And then I need to subtract the divisor of the vertical line at the point A plus BP. And that is the divisor is A plus B P. So let me just write it like this. Do minus here. Plus minus A plus B P minus 2O. Okay, and now I just collect everything. So I collect everything. I get A plus B P plus R minus AR minus BR minus A plus B P plus O. And this is, if you just rearrange, this is A plus B P plus R minus A plus B R minus A plus B P plus O. And if you look at it, this is exactly the divisor of F A plus B, which is the right-hand side. Okay, so it's a bit of it's a bookkeeping basically. There is no hard fact to wonder about. Is the proof okay?
By left-hand side, you meant what is on the left in the formula, right?
Yeah. Yeah. I mean, when I start from the left-hand side because that's the thing I need to really rearrange. But do you follow, Lisa? I mean, I guess you don't have to follow exactly the details of the rearrangement of the terms, but do you see the main principle that drives it?
I don't know. I see a divisor f of A. I see divisor f of B. I know what are the divisors of L and how it is called on the bottom.
Yeah. Here I should say the divisor of FA is this guy, and the divisor of FB is this guy, and then we have the divisor of L APBP,
Right.
and the last one is minus the divisor. This is minus the divisor of VA plus P.
No, everything is fine.
Okay.
Yes.
And then you just check. You just rearrange the terms, and you get FA plus B. Okay. So Nicholas had to leave. So let's. Unless you have questions, we should stop here, and next time we will. I'm pretty sure we will finish the Miller algorithm. Okay, so this, of course, this fact is going to be used. This proposition is going to be used to prove that the Miller algorithm is correct. I mean, that at the end of the day, you get the output is what you expect.
Mm-hmm.
Okay, but it's going to be very easy, I think. Yeah. So have a nice weekend.
Have a nice
Thank you very much.
weekend. Thank you.
Okay, bye. Thank you.
Bye.